Okay, welcome. And this video is for A-level math students for their S1 exam. I'm going to do a series of questions from the latest past papers. I'll call them the challenge questions. I'll do the more difficult ones, the easier ones I'll leave out. There's a basic question on cumulative frequency. I am not going to go on and do that. I am taking you to question number 2, which is slightly challenging. It says Alicia has 4 coins. One of the coins is biased, so that the probability of obtaining a head is 0.6. The other 3 coins are fair. Alicia throws the 4 coins at the same time. The random variable x denotes the number of heads obtained. Show that the probability of obtaining exactly one head is 0.225. So, um, to be honest, the problem with this question is the number of coins and the fact that one of them is biased. So I'm going to say that if I want to obtain one head, there are two possibilities. One possibility is that the head comes on the biased coin, and the one possibility is that the head comes on one of the unbiased coins. So this sort of presents a scenario where I have to think about which coin will have the head when they come up on the unbiased ones. So I'm going to write it like that, and I'm going to explain to you why I'm doing a particular thing. So let's separate the biased head. So let's say the biased head comes up. The unbiased will all have tails. So UT, UT, and UT. And the other possibility is that the biased obtains a tail, and the others are all the others have one head. Now, since I've separated the cases for these, what I can simply do is I can just think about the probability 0.6 into. Now, these three are all the same, so 0.5, 0.5, and 0.5. There's no need to change that order either because I know that all three will have tails. On the other hand, when I'm doing this part, so I get 0.4. But I know that one of these is a head and the other two are tails. Now, I don't know which one. So in this case, what I'm going to tell you is that what I need to do is I need to multiply it by 3 factorial divided by 2 factorial. Why? Because there are 3 letters H, T, T, and I need to divide by 2 factorial because there are 2 T's. That's how I sort of teach the arrangement part of this. Remember that I'm not involving this. Why? Because I've already separated the cases for this. So if you've already separated the cases for a particular category, you don't need to think about its arrangements. You've already considered that fact that it could be a different outcome, and you sort of arranged that. Now, remember that this doesn't inherently say that I am, tossing the unbiased coin or the biased coin first. I am just considering the order because what I want to emphasize is that this head could appear on any of these coins, the first coin or the second coin or the third coin. You will definitely have have a range of coins. It's not that you could take the second coin and toss it first. It's the same coin. It wouldn't make a difference. So that gives me 0.15. Together it gives me what? Together it gives me 0.075 plus 0.15, that gives me 0.225. Then let's just complete the table. Now again, important idea that I need to consider is that 1 is given, 0 is given. I just need to calculate one more of these and then I'll be done with that. So again, I need to think about if the biased got a head, then the unbiased need to have one head and they need to have two tails. Or if the biased did not get a head, it got a tail, so unbiased head, unbiased head, and unbiased tail. So I'm again calculating in the same way that I did earlier. I'm going to say that 0.6, 0.5, 0.5, and 0.5 into 3 factorial divided by 2 factorial. And 0.4, 0.5, 0.5, 0.5. If you're still very confused about why I've done this scenario, you can, sort of draw, take a spare page, take the last page, or you can even draw it here if you want. It's going to be a relatively long tree diagram. You can just draw the biased coin first and then 3 unbiased coin. It's going to be a long sort of solution that way, but I can be absolutely sure that you'll end up with the right answer. Once you do this, you toss up 3 unbiased coins and you can still end up with the right answer. So you can do that if you want, and that should give you the correct answer as well. It's a 16 outcomes. It's going to be a long solution though, but that tree diagram could also help you do the second part of the question. So it's like spending 5 minutes for a tree diagram and then, sort of you have the outcomes there. So let's see what this gives us. 0.6, 0.5, 0.5, 0.5 into 3 gives me 0.225. And that should also give me 0.225. So 2 gives me 0.45. Let's see. 0.05 plus 0.225 plus 0.45 plus 0.075 gives me 0.8. So that should be 0.2. I'm not computing that separately. I'm just checking my answer now. Let's see if I get the correct answer. No, I seem to have made a mistake somewhere. Oh, okay, that shouldn't be 0.225. My bad, calculation mistake. Everything else is correct, I think. Okay, 0.225 plus 0.15, 375. And that should give me, that was 2 heads, sorry, 2 heads. So 0.375 here. And 0.275 here. Okay, that should settle this question. The working was correct, it's just that I messed up the calculations trying to do it in a hurry. I think finding the variance is simple. I'm not going on and doing that. Just apply the formula that you've learned and you should be fine. Moving on to the next question. It says 80% of the residents in Kinwawa are in favor of a leisure center being built in town. 20 residents of Kinwawa, so let's 0.8, n is 20, are selected at random whether they're in favor of the leisure center. Find the probability that more than 17. So this looks like a binomial question. So I'm going to say that I'm asking you for the probability of x greater than 17. So I'm asking you for the probabilities of 18, 19, and 20 are in favor. So 20 C 18, 0.2 power 2, 0.8 power 18, plus 20 C 19, 0.2 power 1, 0.8 power 19, 20 C 20, 0.2 power 0, 0.8 power 20, q power n minus r and p power r. I'm just checking if I am getting the right answer. Okay, I am then going to use my calculator to churn out all the probabilities that I want. Now, again, I've told you this before, having this white calculator helps. So if you have that, it's going to be easier to calculate 18, 19, 20, and n is 20, p is 0.8. So I have my probabilities. This is 0.1369, 0.0576, and 0.0115. I can just then use my normal. I could also have done it all together and it wouldn't have made a difference. So you can do that if you want. 0.206. 0.206. Okay, so moving on to the next question that says find the probability that the fifth person asked is the first person. So I suddenly gone from the binomial to the geometric. Now I'm not talking about all 20 people, I'm just talking about the observations up to the first person who is not in favor of is the first person who is not in favor of the ledger. So my success is now people who are not in favor of the ledger. There were 80% who were in favor and 20% who were not in favor. So I'm asking you for the probability of x equals to 5. So I'm going to say that this is q power r minus 1 and into p power 1. So 0.5 minus 1, sorry, 5 minus 1. 0.08192. Let's check. I've not rounded it off to the correct number of decimal places. So 0.0819. Then it says find the probability that the seventh person asked is the second person who is not in favor. So what that means is that there was one person up till the sixth, so up till the first six people that you sort of asked. So that could have been the first person, that could have been the second person, that could have been the third person, fourth, fifth, and sixth itself. Then the seventh person became the second person. So you know that on the seventh trial, you get a person who's not in favor. But this person is the second person who is not in favor. So the first six have one success. So there are two ways of handling this. One is that I could say that the first six presents a binomial distribution where I'm looking for a person who is not in favor, and I'm going to say that what I want is 6c1 0.8 power 6 minus 1 0.2 power 1 into 0.2. Or the other way of thinking about this is that I could say that the seventh person is someone who does not agree, and among the first six people you have five failures and one success, but they could be in any order. So I'm going to say that 0.8 power 5 into 0.2 into 6 factorial divided by 5 factorial and then multiplied by 0.2. That is what I could also do. They are both going to give me the same answer that I have here. So 0.8 power 5 into 0.2 into 6 into 0.2. 0.0786. Let's check. Yes, that is indeed the correct answer. So remember that this is a merger between binomial and geometric. If you have worked through the worksheets that I attach in my book, there are questions like that from other boards that were there in the worksheets, and that was my assumption that at some point this is going to be tested in the past papers for you as well. Okay, moving on. I have question number 5, a very tricky question, to be honest. When I was doing it for the first time, I had real trouble, sort of visualizing a way to do this question. I could sort of figure out what was happening, but it was difficult to visualize a way. It says Marco has 4 boxes K, L, M, N. He places them in a straight line in that order. Now Marco has one colored marble, one is red, one is green, one is white, and one is yellow. He places a single marble in each box. Events A and B are defined as follows. The white marble is either in box L or box M. So the white marble could either be here or here. So that's the simple probability. If it doesn't matter what the others are, you could just say that the white marble being in this could be 1/4 and this could be 1/4 as well. So together they make 2/4, which is half. So the probability of A is basically half. Then B says the red marble is either is to the left of both the green marble and the yellow marble, which means that now this is something that sort of poses a lot of questions. Now I will have to think about the order, which means that I will calculate my probability using permutations. So what I want is I want the red marble to be on the left of the green and the yellow marbles. So I'm going to say that the red could be here and the green and yellow could be anywhere here. So that gives me what? That gives me 3 factorial, and the total number of arrangements is 4 factorial. Or it could also be a possibility that the red is here and the green and yellow are here, but in any order. That automatically means that the white needs to be here. So another possibility is basically 2 factorial divided by 4 factorial, because both white and red have gotten fixed. So 3 factorial over 4 factorial gives me 6 over 24, gives me 1 over 4. And 2 over 24 gives me 1 over 12. So together they make 1 over together they give me 1 over 3. So that's the probability of B. Then if I want to think about whether they are independent or not, remember that you have to think about whether A intersection B should E is equals to probability of A multiplied by probability of B. Now I've thought about probability of A, I've thought about probability of B. How does A intersection B fit here? Remember that both events have to be satisfied simultaneously, which means that W can only appear here or here. So this condition automatically gets discarded. What two conditions am I talking about? That the red is here and the W is here, which means that the green and yellow should be here. That's one arrangement, but they can sort of, shuffle around. So I can say that that becomes 2 factorial divided by 4 factorial. So I'm calculating the intersection now, or the red and white could be here, the green and yellow could be here. So that's another 2 factorial divided by 4 factorial, because only the green and yellow can change places. The red has to be fixed, the white has to be fixed, because they both need certain conditions to be satisfied. So that gives me 2 over 24 together. It gives me 2 over 24, which is 1 over 12. So the probability of A intersection B. Let me just think about if I'm forgetting something. Because this is indeed a tough question, I just want to make sure. My alarm is also ringing, so just let me put that off. Okay, I seem to be forgetting something when I'm talking about the intersection. Because I don't seem to be getting the right answer there. Okay, no, I think I calculated wrong. Yeah. 2 divided by 24 gives me 1 over 12, so that's 2 over 12, not. So yeah, that's what I was getting wrong. Okay, 1 over 6. So A intersection B is 1 over 6, and A is half, and B is 1/3. So let's see if I get 1 over 6. 1 over 6 equals to 1 over 6. Those are equal. Therefore, A and B are independent. Okay, let's move on. See the next question. Okay, let's see question number 7. It says find the number of different arrangements of the 9 letters in the word delivered, in which 3 A's are together and the 2 D's are not next to each other. Okay, so I have a habit of writing it like that. Okay, so the 3's are together, so that's in a box. And the two D's are not next to each other. So what I'm going to do is I'm going to first write the other four, 1, 2, 3, 4, and then a dash underneath it. That gives me 5 factorial. I go into the box, that gives me 3 factorial. I'm going to divide by the identical ones. Let's just first write them down. And then I'm going to say that what the D's can do is they can step here, 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 and here. So those are 6 places. So that becomes 6c2 into 2 factorial. They're also identical. So divided by another 2 factorial. Let's see if that gives us the correct answer. 5 factorial into 3 factorial into 6c2 into 2 factorial divided by 6 divided by 2. So I am getting 1800. Is that the correct answer? Yes, that is indeed the correct answer. Okay, then I seem to have solved this earlier, so I'm just going to erase that and come back and solve it again. Let's just find the probability that the randomly chosen arrangement of the 9 letters in the word delivered has exactly 4 letters between the two D's. So 4 letters between the two D's, 1, 2, 3, 4. D, and there were a total of 9, so I've written 6, 7, 8, 9. So there are other possibilities then as well, that the D could appear in the second position, and then D could the other one has to move there as well, because I need exactly 4 between them. So D and then another D. So what that gives me is all of these are sort of then identical arrangements. The D's are fixed. So that gives me room for 7 factorial, but 3 of these are E's, so 3 factorial, so 7 factorial over 3 factorial. That is also 7 factorial over 3 factorial, 7 factorial over 3 factorial. Remember that there are old dashes here that I haven't sort of drawn, but that's what it means. So 7 factorial divided by 6 into 4, that gives me 3360 on the total. Let's see if I get the correct answer. Oh, I needed the probability. It says find the probability. Okay. So probability is therefore then unrestricted arrangements at the bottom. So 9 factorial over 2 factorial into 3 factorial. So that gives me 3360 over 30240. So 3360 divided by answer, and I get 1 over 9. That's my final answer. Okay, then this last one, this was a little tricky, so I solved it earlier. Let's solve it again. It says 5 letters are selected from the 9 letters in the word delivered. Find the number of different selections if the 9 letters include at least one D and at least one E. Whenever you're doing selections like this and you have identical letters, what you need to be aware of is that you need to uh, separate the cases. So 1D and 1E, and then sort of increase from there. So 1D and 1E, then 2D and 1E. So then 2Ds and 2Es. In fact, let's just make it more logical. So 1D and 1E, then 1D and 2Es, then 1D and 3Es. Then 2Ds, that's the case with 2Ds and 1E, then 2Ds and 2Es, and 2Ds and 3Es. That's the easiest case. You have one here. You're left with one number here, so you're going to say that this is basically how many letters am I left with? 4. Okay, 4C1 and 4C2, 4C1, 4C2, 4C3. 4C3 is 4, 4C2 is 6, 4C1 is 4, 6, 4. Let's take a total. That should give us 25. That's the right answer. So always construct your cases properly. That should give you the correct answer. Even writing the cases carries marks. So make sure that you do this properly. 1 mark is for the cases. The second mark is for the combinations, and then 1 mark is for the correct answer. Okay, that brings us to the end of this exam. Let's move on and see some questions from the next exam before we end this session. Okay, 50 values of the variable x are summarized by these. Okay, unusual sort of data, never seen this kind of before. One of them is adjusted, the other is not. Find the variance of these values. So what I want to calculate is the variance of x. So variance of x is basically sum of x squared divided by n minus the mean of x squared. But I don't have the mean of x squared, but I have some adjusted data. So I'm going to say that on the right hand side, I'm going to start calculating. I'm going to say that the mean of x minus 50, x minus 20, sorry, x minus 20 is the same as mean of x minus 20. If you don't know this, there's another marathon that I did on these questions. I solved about 8 questions there. You can go back and see that, and you should understand that. So this gives me 35 over 50. I don't know the mean of x, so minus 20. So 35 divided by 50 plus 20. That gives me x bar equals to 20.7. I hope that's the correct answer. Okay, then sum of x squared is 25036 divided by 50 minus 20.7 squared. It's giving me 72.23. Let me check if that's the correct answer. Sounds a little odd, but these questions are generally that way. Number 52. Okay, November. Yep, that's the correct answer. Okay, coming back. Let's do this one. It says the pair four-sided spinners each have sides labeled 1, 2, 3, 4. The spinners are spun at the same time, and the number on the side on each spinner lands is recorded. The random variable x denotes the highest number recorded. Show that probability of x equals to 2 equals to 7 over 64. So I have three fair-sided, four-sided spinners. So I'm spinning thrice. So there are 3 outcomes, the highest of which has to be 2. Now, the important thing about this question is that if the highest is 2, that doesn't mean that the other two have to be less than 2. They could all also be 2. So I could say that the one set of outcomes could be 2, 1, 1. The other set of outcomes could be 2, 2, 1. And the third set of outcomes could be 2, 2, 2. So these are the 3 outcomes that would give you the highest score as 2. So 1, 2, and 3 outcomes. So what's the probability of getting the first two? 1/4, then 1/4, then 1/4. They could come up in any order. So 3 factorial over 2 factorial. So again, 1/4, 1/4, 1/4, then 3 factorial over 2 factorial. Then 1/4, 1/4, and 1/4. And then 3 factorial over 3 factorial, because all of them are identical. So that gives me 3 over 64, 3 over 64, 3 over 64, sorry. And then 1 over 64. So together I make up 7 over 64. So that's there, shown already. Now complete the probability distribution. Now the easiest to do is probably 1. Why? Because 1 can only occur when all of them are 1, because the highest has to be 1. So I'm just going to go on and calculate that. That's 1 over 4, 1 over 4, and 1 over 4. and that gives me 1 over 64. Once I have that, I don't really need to compute 4 because that's a long and tedious process. 1 plus 17 plus 19, 64 minus answer. That gives me 37 over 64. I will still check my answer just to be sure that the gimmick that I employed has given me the right solution. 1 and 4. Yeah, that is the correct answer. Then this next question basically Then this next question is basically on another occasion, one of the four-sided spinners is spun repeatedly until a 3 is obtained. Okay, so I'm looking at the first success. So I'm looking at 3. The random variable y is the number of spins. So this is a typical geometric progression. So I'm going to say that my success is 1/4, my failure is 3/4. One of the first four-sided spinners. I'm not spinning 3 spinners anymore. So I'm going to say that this gives me 3 over 4 power 5 minus 1 and 1/4 power 1. So 3 power 5 minus 1 divided by 4 power 4 divided by 4. So 81 over 1024. Let's check. Uh, 243 divided by, okay, that's 6 minus 1. My bad. 6 minus 1. That's what I was thinking. Why can I get this simple answer right? So that's 3 power 5 over 4 power 5 into 1/4. 243 over 4096. 243 over 4096. Then y is greater than 4. So you must remember that there is a formula for greater than, and that formula is that if x is greater than r, for geometric progression, this is just q power r, so x is greater than 4. So that's just 3 over 4 power 4. You could also, sort of take 1, 2, 1, 2, 3, and 4 and then subtract it from 1 and you're going to get the same answer. But this is an outcome that you should remember. So make sure that you remember that. 81 over 256. Okay, then okay, so then this question says find the number of different arrangements of the 9 letters in the word activated. So activated, let's just write that down first. So that's 9 factorial over 2 factorial into 2 factorial, and that's simple, I think. 90720. Okay, yeah, that's correct. Then I have, this is find the number of different arrangements of the letters in the word activated. Activated. Okay. In which there are at least 5 letters. So that gives me a number of arrangements. 1, 2, 3, 4, 5, and then A, and then 2 more. Then I can have A here, and I can have A here. Then I can have A here and A here. But this is at least 5, so I could have another set of arrangements which has 6 in the middle. And then A here, and that could also lead to 2 different arrangements. And then there's a third arrangement where I could have all 7 here and an A here. So that's 7 factorial. The t's are identical, so over 2 factorial. All of these are the same. They're not different. They're just the same outcomes. How many outcomes do I have? I have 6. So 6 into 7 factorial over 2 factorial. So 6 different cases. 6 into 7 factorial divided by 2. 15120. Then this last question is the trickiest. And I've solved it on the board. This is one way of solving it. I'm going to do the other way right in front of you. So this says 5 letters are selected at random from the 9 letters in the word activated. Find the probability. Now, when you have selection of certain letters and you have probabilities, there is that change in idea. Now, we've seen before that I have always told you that there are no selection for identical letters, but that concept sort of has to change when you're computing probability. What I've done on the board is another method that I explain in a different video, and I will tag that video. But and there's a question called tomorrow where I sort of explain this concept as well. That question has the word tomorrow, but I'm going to use I'm just going to tag that video and you can go back and see it. But at this point, I'm going to teach you how the marking scheme tells you of how to solve this question. So activated, and 9 letters and 5 letters are to be selected. It says that the selection does not contain more T's than A's. So I need to have a less number of T's and more number of A's. So what I've constructed is 6 different cases for it. I want you to understand the cases first, and then I'm going to compute a probability for it. So A and no T's. So there's one A and there are no T's. There are two A's and there are again no T's. That also satisfies the condition. This is one A and one T. So it could not be more than, it could be equal to. So two A's and two T's is another case. I need to stay. Then there's another case that no A's and no T's, and I sort of missed out a case, so I've written it at the end where I have two A's and one T. When you are doing such a question where you want to calculate the probability of identical letters which are being selected, see, if you're calculating just the number of ways of doing it, you shouldn't be selecting identical letters. But if you're doing probability, what you can do is, I've told you before that this leads to double counting. So it could lead to double counting both in the numerator and in the denominator. So let's say I am taking case number 1 where I have A and no T's. I could say that there are 2C1 ways of selecting the A's, and there are I don't need any T's. So how many letters are there? 1, 2, 3, 4, and 5. So that gives me 5C4. So that gives me 10. The second case is no A's and no T's. So two A's and no T's. So that's 2C1, 1C1, and then 5C3. So that gives me another 5C3 is 5 into 4 into 3. That gives me 10 as well, I think. 5C, yeah, 5C3 is 10. Let me just check. 2 A's and no T's. Yeah, 5C3. Okay, in fact, I've done sort of arrangement. I should do a bit different. Okay, for this second case, so two A's and no T's. So I need to select two A's, both the A's get selected, and the no T gets selected. So 5C3. I needed two more. So 5C3 into 1 gives me another 10. Okay, then moving on to the third case, I have what do I have? A and T. So I'm going to write A and T. So one A needs to get selected, one T needs to get selected, and I again need 3 more. So that gives me, if I see 3 is again 10, 10 into 4 gives me 40. Let me check if I'm doing it correctly. A, T, and yes, I'm doing it correctly. So then I have T, and T, and one more. So both A's get selected, both T's get selected, and then I have to select one more. So 5C1, 5C1 gives me 5. Case number 6, no A's, no T's. So what gets selected are all the other 5 letters, 5C5, that gives me 1. Then 2 A's, 1 T, and 2 more. So 2C2, 2C1, and 5C3. So that gives me 20 as well. So together I have, let me check, 20, 40, 80, 86. So I have 86 different outcomes that satisfy my condition. But I was not looking for the number of outcomes. I was looking for the probability. Now you should also remember that I've double counted a lot of outcomes. So what I'm going to do is I'm also going to do that double counting. I'm going to say that the denominator is then simply going to be 9C5. Remember that you are only going to do this when you have a question that asks you for the probability of selecting letters when the letters are identical. If you are not asked to select letters, if you are just asked to select letters and you are asked for the combinations, remember that in the question that I did in the earlier paper, for example, this question, this is where I don't go on and select D's or E's. Why? Because I'm uh, calculating the combinations. I am not calculating the probability. I will be back with some more questions. There is this video on my YouTube channel that has the word tomorrow in it. If you search it, you will probably find it as well. And that is where I explain this other method of doing the question, which also gives me the correct answer. So you can go back, review that if you find that easier. Understanding that easier, that's the other way of doing it. It's not in the marking scheme, but it was there in the examiner report in the question that was there before. So try it out if whatever you feel comfortable with. Since it's a 5-mark question, it's supposed to be difficult, and there is no other way of doing this question. So make sure that you understand the concept. Please make sure to like and subscribe. I will be back with another set of challenging questions before your exam. Thank you.